Hi all, my name is Arav, this is Vivek, and we are part of upcoming rookie team for the center stage season, Marksmen 23381, and we are presenting on our off-season coaxial swerve. So let's just go into the definition of a coaxial swerve. But first, a swerve is just any drivetrain that you can rotate the wheels in. So just think of a shopping cart and the wheels are actually powered. And the coaxial part is that the power transmission for the wheel is in the same, is in line with the module rotation.
Okay, so we're gonna explain the coaxial bit of the swerve. So the way it works is you need to rotate the pod that the wheel is in, and you have to rotate the wheel. So we have it broken apart by color. The blue will turn the pod of the wheel just through the gears, and then the like pink, red will turn the wheel itself through the bevel and spur gears.
So one question that we get is, why did you build a coaxial swerve and what's the inspiration for it? So the main inspiration for this drivetrain was from KookieBot's 16379. They had one of the first competitive coaxial swerves last year, and that really inspired us to make our own and take on the challenge of making one. And then the benefits over a mechanism drivetrain is that we're able to direct 100% of the force in the direction of the wheel, and it's not as easily able to get pushed. So the problem with mechanisms are that strafing is actually slightly slower than going forward and back, and also the rollers make it super easy to push the robot around. A disclaimer for this presentation is that this is not a guide for building a coaxial swerve. This is just a showcase of our progress and lessons we learned. And the reason is because this was recently built like in the past week, and we haven't run this in competition. So until then, we can't really give a guide on how to build one.
Okay. So now moving into more of the design of like how the swerve actually works. Okay, so here's just some specs. The drive ratio is 9-to-1. Using the 6K RPM bear motors from GoBuilda. We have 1-to-1 with Axon Minis. Those are the only servos that can do rotation because they have analog output. And then we have ThriftyBot 3-inch bearings. They're X contacts, so they're most optimal for like this use case. We also have 3D printed wheels with gray grippy tread, and then one plate holding it holds all the modules, and it has all of the other parts based off of that one plate. Okay, so explaining the power transmission of like how we get from the motor and the servo to like actually like rotation. So starting off with the servo and the rotation of the pod, we have we're using a gear to gear and then a pulley to gear. And we do instead of just like most teams will ask us, why would you just not put a pulley to the pulley, just make it simpler? And that's because of sizing. It's a lot smaller and more compact if you use gears, because the ratios aren't like as big. So we use gears to keep the form factor small, and then the belt we use is a GT2, and we use GT2 over HCT. Just because it's more efficient to use the GT belts. And so for the wheel transmission, this is a little bit more complicated. And so basically, we have the motors over there, and from the pulleys on the motors, we go to a axle that you can see in the center of the pod there with a pulley and a gear on it, and that axle will spin. And then there's a side one on the outside, coming out of one of those like forks right there on the side, and that has another gear and a bevel gear on it. So there's quite a few layers of power transmission, and we have a video showing you kind of visualizing it. It's a little bit easier to see. So I'm just rotating the belt here, and you can see the wheel rotating. Let's run that one more time. to see how all of that goes together. And then for the Swerve drive actually driving, we have it on the next slide. The quality. So you can see it's quite quick when it's strafing and spinning as well. So yeah. You got it.
Next is programming, how to actually get this thing working. And I'm going to keep this a little brief because I believe Kooky Boss have already mentioned a lot of this already. So the goal of this is to back slide. All right, so the goal of this is to take the X and Y speeds from the left joystick and the rotation speed from the left joystick and the rotation speed from the right joystick and combine it all to calculate the speed and angle for each module. So we use inverse kinematics from a 2011 FRC paper to do all the equations in driving. And this allows us to take the chassis speeds and rotation into module speeds and rotation. And then we also use the IMU to convert to field centric for easier driving. So this is the paper that we used. The gist of it is that given the vehicle rotation and translation, we're able to calculate each pod separately, and we implement that so that the pods actually move to that position and speed. So these are the equations. It looks pretty complicated, but a lot of these things are repeating. So we are able to easily simplify this into 4 main equations, A, B, C, and D up top. So we split up the vectors into X and Y components for calculating it better. And with these 4 equations, next. We just do simple trigonometry. So just using arctan, we're able to get the angle of the vector. This is where the pod has to rotate to, and getting the hypotenuse of the triangle, which gives us the speed of the wheel. So just the inverse kinematics will get the Swerve working, but it's not optimal at all. And it will drive pretty strangely. So we have to have a lot of optimizations. The first is implementing motor flipping. This means that in the picture up top, instead of having to rotate left 135 degrees, we can just rotate right 45 degrees and then reverse the motor spinning backwards, and it gets us into the same position. And that makes our max rotation from the servo required from 180 degrees to 90 degrees. Then we also, so another big thing with Swerve is that you have to have very fast, fast loops. So this means that you're updating the control algorithm constantly. And we did this by implementing bulk reads. This reduced the loop times a lot and makes our Swerve easier to drive. And then we also have slew rate limiters, which limit the change in input from the joystick. And this makes the Swerve less twitchy and more smooth movement.
So since Swerve is fairly complex, there's a lot of hardware challenges that we faced when building this. So we had some issues with the bearing tolerances, and that can be easily fixed by just recutting the plates. But the biggest issue we've had is gear meshing. We've had a lot of issues with gears just not meshing properly and really grinding against each other, which leads to a lot of friction, varying friction on the on the wheels or on the pods, and that can just make the Swerve just inconsistent when you're driving it. Another issue we've had is like the wood. It's currently, most of the plates are made out of wood right now, and it just flexes a lot, which is not optimal when you have bearings and you're turning a lot. And so and then the last issue that we faced was the set screws on our pulleys were rusted. This is more of just a specific issue that we had, but just wanted to mention it.
And then for the software, one thing that we had to get used to was the Axon analog outs. One thing we didn't realize was that you have to actually power the servo for the analogs to work. So you can't just have a not running servo and just move it with your hand. That doesn't work well. Also with the inverse kinematics, we thought that counterclockwise was positive rotation, like a unit circle, but actually clockwise is the positive direction. And then a lot of the tuning with the swerve was just figuring out what to reverse, what servos to reverse, what encoders to inverse, what motors to inverse. So it was that took a majority of the time for programming the thing.
Okay, so we want to iterate on our swerve and make it better and more consistent. So one way of doing that is adding an SPM for the servos for the rotation, and that allows us for faster rotation of the modules and just getting the most out of the servos. We also want to switch to aluminum plates. We've just used wood right now because it's quick to prototype with, but we want to switch to aluminum plates so that we get rid of that flexing issue. We want to add odometry so we can have consistent, autonomouses. We don't have it mounted on the robot right now. And then the big thing that, the biggest issue that we faced and the one that we want to keep on addressing is the mesh of the gears. And we just have to play around with the spacers a lot. Even though, one thing might be true in CAD, it doesn't translate to the real world, and parts, might not turn out exactly, as you plan them in CAD. So you have to kind of play around with the spacing a little bit.
And then for the software side, the first big thing is just tuning the PIDs more. I'll blame most of this on the hardware because we have like varying frictions between the modules, so not every wheel turns as easily as others. Also implement odometry and actually get position tracking on this. And right now we only have a teleop, so we would like to try out autonomous and see how that goes. And then just trying to reduce loop times with photon and IMU multi-threading. Then maybe we might implement second order kinematics. So the conclusion, so we spent around 3 weeks to a month on this swerve. Most of it was just CADing, and then in the last 2 weeks has been assembling and programming. But we definitely feel like Swerve has a place in FTC as a option as a drivetrain that can be very successful. And I feel like one thing we did was we underestimated the amount of iterations that has to be made for Swerves to work well. So I think most of the iterations were done in CAD, but I feel more physical iterations would help solve a lot of the issues we were facing. And then assembly as well, it was a rush getting this ready for today. And then we feel like overall this has been like a very good teaching moment for us. We're both seniors going into our last season, so we wanted to just try something different, try something that can teach us new things and challenge us. And this Swerve has been that for us. And we would recommend it if you do have the time, money, and personnel. But I feel like most teams probably don't have all those three things. So Swerve is right now for us has been a very interesting project, and we hope to iterate it and improve it for the future for the next season. So here are just some of the resources we use and recommend. And then, so a lot of it comes from FRC because that's where Swerve is most prevalent. And then credits, if Vivek wants to.
Yeah. Just credits to Veer from CookieBots. He helped us out with some of the design stuff on the CAD, and then just answering like all my questions that I had, and then Alex from Technodotes just helping out with just any questions that we had as well. So we just want to thank both of them, and just CookieBots for coming up with the Swerve, inspiring us all to make one. So yeah, that's about it. Thank you.
In person. Do we have a website yet? We can. Yeah. I think there's a recording of this, so I think that might be the easiest way to get the URLs. So just going through the recording and finding the slide because we don't have like any website or anything for this.
We can
FLYSET?
find a way to get it out.
We'll try to share it to FLYSET.
Are there any other questions?
Any in-person questions before we move on to online questions?
Yeah, so is the default setting here of driver-centric program?
With the kinematics, it is driver-centric. And what the main benefit with Swerve is that you have the same amount of power in each direction. So that's why a lot of teams do field-centric with Swerve, and it's just more intuitive. So, but driver-centric would definitely work. But while driving this, we realized that turning is very twitchy. So field-centric is probably easier to use if you want to drive it. Any other?
You're just saying like there's different friction on the wheels. Yeah, so that's due down to like gear mesh. So depending on how well some of the gears are meshed, like the bevels especially, you can get varying friction because like some of them will be slightly grinding or something together because they're not like perfectly meshed. You have to play with the hardware. Like I said, you have to mess around with the spacing a lot of like where it's spaced on the shaft. Like in CAD, I have it one way, but like I said, it doesn't always translate to the real world, and you just have to just play around, guess and check with the values just over and over. Any other questions? Okay. Yeah, sorry. So all of the gears are from GoBuilda. They're all metal, steel gears. Yeah. Yeah, they're all metal gears. Most of the pulleys, yeah, including the bevel gear, are all metal gears. Okay. See a question. You want to answer that?
We personally haven't tested any autonomous or Roadrunner yet, but we know from I think Alex had experience with his Swerve last year with Roadrunner, and the main issue with using Roadrunner with this is that it assumes that the modules rotate instantaneously, which is not true in the real world. So when you have like sharp corners or arcs, it'll probably like go out and like curve around it because the modules take time to rotate. We haven't fully timed or tested it, but right now it's enough time to make it an issue, but hopefully with SPM, the servos can be faster and that'll cut out a lot of that error. It can be used, but I don't think it's optimal for this type of drivetrain without significant modifications to it. Let's do online questions. One more.
Yeah. So when you're controlling the Swerve drive, I've noticed that in your demonstration video, the robot will actually turn. When the robot turns, does its orientation also turn like in the code? So, for example, when you tilt the joystick forward, right? I'm assuming how you drive it is it's got all directions. You have one joystick when you point it forward, the robot goes forward, correct?
Yeah.
So when you point the joystick forward after the robot is turned, will it go in the direction that the robot has as its forward?
Yeah, so yeah, that's correct because we are using field-centric control. So field-centric takes in the IMU of the robot itself and then offsets our input vector. So that means that even though the robot turns, forward on the joystick will go forward away from us and back on joystick will make it go close to us no matter the orientation of it. Let's do all right, so we're gonna do a couple online questions that I saw. One was dimensions and one was like yeah, I think just one question was dimensions of this sort.
So one of the online questions I think was the dimensions. It's like roughly 13 by 13. Yes, it's roughly 13 by, it's like 13.1 by 13 by 0.1.
I think that's it.
That's all?
Yeah, it doesn't show up here. I don't see any here.
It says.
What is the line for what you use first? Magnum versus Swerve.
Macadam versus Swerve. So someone said, how do you feel about Macadam versus Swerve? Well, after building the Swerve, I feel I don't know. It's probably less likely that I would actually want to run a Swerve in competition just because there's so many things that can go wrong on the drivetrain, and Macadam is much easier. It's just much easier to just make than Swerve.
I would say that don't go into a Swerve expecting it to be good right out of the gate. You should really be going into it with the mindset of learning and having this be a project that you can constantly reiterate on. While with Mechnum, the main benefit of Mechnum is that is very well thought out already, and it is very easy to get it working on the first go. And with a drivetrain, you would hope to have the most reliability out of that component.